Here we are going to discuss the crystal. What is a crystal? Now, crystal is combination of two things. That is, one is the lattice and the basis. Now, the lattice is the related to the structure and the basis is related to the component, okay, or the constituents. That means what the crystal consists of. Now if you consider this 2D lattice, this is the origin of the lattice what we have, and each point here, this is called the lattice or the lattice structure. Okay, now bases are what we are placing at the each points or the nodes here. These are the bases. Now how do you form this structure? Now this structure is formed from a vector called translational vector. So this is translational vectors, okay, or translational vector. Now what or how you can define a translational vector? Now if you consider this as the lattice is the nothing but the arrangement. You can say it is arrangement of something. Okay, so how you are arranging this is some with some periodicity, or you can say it's a periodic arrangement. Now formed by what? It is formed by the translational vector. Now consider this as the two dimensional lattice. If this distance is a and here you have b, now any point on this lattice, say for example t, or you can take this as some t. Okay, so t can be written as some n times a plus or n1 times a plus n2 times b. Now in this case, this is what our x-axis says, and this is what our y-axis. So this is 3 times a and 1 and 2 3 4 times b. So you can write it as t is equal to 3 times a plus 4 times b. Similarly, any point, for example this point, can be written as 3 times a plus b. So this is called translational vector t. You can write this one as t1, this one as t2, or any point here you can write it as 3 comma 3, which represent 3a plus 3b. Coming to the three-dimensional lattice, we can have this as the center of this lattice, one end of the lattice. Now this is a, and here you have b, and here you have c. Okay, in all directions x, y and z we have a, b and c. Now any point on this translational lattice or the sorry, yeah, this lattice, we can have the translational vectors given in this form telling you t1 or t is equal to n1 times a plus n2 times b plus n3 times c. Now a, b and c are uh, the lattice constants. We will name them as a, b and c are lattice constants. Okay, so any point on this lattice, this is a three-dimensional lattice, and any point on this three-dimensional lattice can be represented by the translational vector t, which is given by n1a, n2b and n3c, where a, b, c are the lattice constants. Now coming to what is basis. Now, as we have said, bases are the constituent particles in the lattice, in the crystal, we have to say in the crystal, and in the crystal, which you can say which occupies the lattice, okay, which occupies the lattice. Okay, so now what all can be the basis? This basis can be group of atoms, or it can be a molecule and or ion. Okay, so and this basis has to be identical. Okay, it has to be identical in composition, which means at one point it for example, you have this as the three-dimensional lattice, and at some point you have one particular atom A, and you have here atom B, and in another point in the lattice, somewhere in the middle, you have another point C, or the another molecule C. No, it has to be in identical in composition. Okay, and it also has to be identical in arrangement and the orientation. Okay, now as we have discussed this crystal in a hole, this is sum of the basis and the lattice. Okay, so this is what in general is about the basis. One more thing we can discuss here is if the crystal or the lattice points, if the each lattice point have identical surrounding, then the lattice is called Bravais lattice. Let us discuss what is a unit cell. Now unit cell is the smallest cell from which the entire crystal can be constructed, from which the crystal can be constructed. So now if you have something like this, okay, now this is a crystal. Now this is the unit cell, and similarly you see, let us draw a few more dots. To make it more understanding the unit cell. Now this is a unit cell, and similarly this is another unit cell, and this is also a unit cell. Okay, now yeah, these are some examples of unit cell. Okay, now this unit cell has 4 corners and one 4 corner atom and one atom in the center, so it has more than one atom in the cell. Okay, so this is an example of unit cell with more than one atom, and this one is an example of unit cell with one atom, and this is called primitive unit cell. This is because it has got only one atom. This is called a primitive unit cell or one atom cell, and this is also called a Wegener Seitz cell. Okay, now here you are finding another unit cell which has a total of 4 corners and 4 into 1 by 4, that is one atom, so that is one atom. So this is called primitive again, but it is not Wegener Seitz cell. So you can understand the difference between Wegener Seitz and primitive unit cell here. Okay, now just a discussion on what is Wegener Seitz cell. Now it is a cell, a unit cell basically. We can write unit cell, which is primitive. Again, we can write more precisely, it is primitive, which again means there is the number of atoms equal to 1, so that is why it is primitive. And this is one such primitive primitive unit cell which is closest to the given lattice. This is the smallest possible cell, closest. Again, there is a condition which should be closest to the here given lattice point. You have to write given lattice point to the given lattice point. Again, about the reciprocal lattice of Wegener-Seitz cell, a reciprocal lattice, we have the Wegener-Seitz cell. We will write WS cell in reciprocal lattice. Reciprocal lattice is called first Brillouin zone. First Brillouin zone. For the three-dimensional lattice, we have here first one as a simple cubic. It is sometimes represented as SC, and in SC what happens is here you have one atom. All atoms or the molecules are placed at the corners of the lattice or the unit cell. So this is a simple cubic unit cell. So this is SC, which is, and this is a primitive unit cell. Now why it is a primitive? Because it has the number of atoms n as equal to 1. Okay, now coming to the second one, that is here we have the body centered cubic. And along it has all the corners of this cell filled, and along with that, at the center of the body of the unit cell you have another one more atom. Okay, so this makes the body centered, and it is represented by BCC, and it is not a primitive because n, the number of atoms here is 2, and it is represented by I. So here you have primitive which is represented by P. This is I. Okay, so I represent the body centered cubic, and it has total of 2 atoms. One is placed at the center. Now coming to the face centered cubic. So cubic, it's a unit cell with as we began, there is 4 atoms which is at the 8 corners, placed at the 8 corners of the cube, and along with that, in all the faces, this has got 6 faces. The cube has got 6 faces, 1, 2, and this is 3 here, and 4 here, 5 and 6 here. Okay, so all 6 faces being there, so total number of atoms It is represented by FCC or simply F. Okay, so FCC is having number of atoms n is equal to, so four corners at the end, so that is constituting the one, and six atoms on the face which constitute half of the atom, so which is nothing but 6 times half, that is 3, so 3 plus 1 gives you 4. Okay, now the last is base centered. And here the corners of the cube are filled by one atom, which constitute 1 by 8th, and on the face, the base and the top have one atom present, which makes the total of number of atoms is 2. This is constitutes half, this constitutes 1 by 8, so total number of atoms will be equal to 2. Bravais lattice, this is what we are going to discuss. Bravais lattice. Now Bravais lattice is can be identified by looking at the surroundings of the lattice points. Now if the lattice points have identical surrounding, then this particular point is called, or the lattice is called, Bravais lattice. Okay, so this is the idea. And now let us discuss for 2 dimension what are the Bravais lattices. Now first one is the square. Now square we have now in 2D we have 2 lattice constants. Now lattice constants in 2D are A and B. Okay, along x-axis or along y-axis you can say this is A, B, or according to the crystal. Okay, now square we have A and P, and here A equal to B, and the angle between them, A and B, we let us call it as gamma, which is equal to 90 degrees. So this is what is called the square. Now we have the rectangular lattice. Rectangular, A equal to B, sorry, A not equal to B, and the gamma equal to 90 degree. Now 3, and here you have a rectangular centered, and here we have again A not equal to B, and gamma equal to 90 degree. 4, this is a hexagonal. You have A equal to B, and the gamma value is 120 degree. Okay, now 5th one is oblique. Where A not equal to B and gamma not equal to 90 degrees. So this is oblique. Now in general we have in 2D lattice there are 5 Bravais lattice. and you see in from gamma rectangular and rectangular centered there is no difference in the properties, but only thing you have one atom present at the center. Okay. Coming to three-dimensional Bravais lattice, let us start with the cubic, which tells you A equal to B equal to C. So A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degree. Now what is alpha, beta and gamma? Let us write down here. Alpha is the angle between B and C. Beta is the angle between C and A, and gamma AB. Okay, so cubic is A equal to B equal to C, and alpha equal to beta equal to gamma equal to 90 degree. Then what are the structure available? There is a primitive structure of cubic available. There is a body centered as available, and there is also face centered available for the cubic structure. Okay, now so once again this is P for simple cubic primitive, and I for body centered, and F for face centered. Okay, now here we have tetragonal. Tetragonal also we have A equal to B equal to C, and sorry, here tetragonal not equal to C, and alpha equal to beta equal to gamma equal to 90 degree. Now here also we have P, which is primitive or simple cubic, and I, which is body centered, but we don't have F. Okay, now okay, so that's it. Now we have orthorhombic. Here the lattice constants are not equal. Alpha, beta, A, B, C not equal to each other, and alpha equal to beta equal to gamma equal to 90 degree. And in this crystal we have the simple cubic, body centered, face centered, and the C, which is base centered. Now this is C we can write, and what is we will write what is P. P is simple cubic. Okay, then I is body centered cubic. F is face centered cubic, and C is the base centered cubic. Alright, so now we have orthorhombic and the rhombohedral. Rhombohedral, which says A equal to B equal to C, and alpha equal to beta equal to gamma, but it is not equal to 90 degree, and it has only one crystal structure, that is the simple cubic. And this particular rhombohedral is also called trigonal. You can trigonal. Okay. All right. Now you have hexagonal over here. Hexagonal has A equal to B not equal to C, and alpha equal to beta equal to 90, and the gamma value equal to 120. And here also you have only the P, which is primitive or the simple cubic. Coming to the monoclinic lattice. So monoclinic. Here we have A, B, C not equal to each other, and alpha equal to gamma equal to 90, while beta is not equal to 90. Then the structures that we have here is the primitive and the body centered, simple cubic and body centered. And now we have triclinic lattice structure. Alpha not equal to beta not equal to gamma and not equal to 90 degree, and A not equal to B not equal to C. And here you have only primitive structure. Now here you can see all the three-dimensional cubic Bravais lattices, and for cubic we have the PIF. There are three structures available for cubic: tetragonal 2, and orthorhombic we have 4 structures, and for rhombohedral we have only primitive structure. And here for hexagonal primitive and monoclinic we have 2 structures, and for triclinic we have 1. Now if you add all these, 3 plus 2, which gives you 5, 9, 10, 11, 12, 13 and 14. So in total there are 14 Bravais lattice in 3-dimension lattice, 14 Bravais lattice in 3-dimension, while there are 5 Bravais lattice in 2-dimension. When you are preparing for this exam, you must be knowing the different structures available in different type of cells, and the different type of structure available in all these cells. Simple cubic cell. Simple cubic cell, which is, you write it as SC. One example of a simple cubic cell is polonium, and the lattice vectors of a simple cubic are very simple here. That is, vector A equal to AX cap, the B is equal to, again it is BY cap, and for C it is CZ cap. And this A, B and C in the simple cubic cell are same, so we can write A equal to AX cap, B equal to AY cap, and C equal to AZ cap. Then we have the volume of this lattice cell, simple cubic lattice cell volume is equal to a cube. Okay, now the number of atoms equal to 1, and the coordination number is equal to 6, and radius of the atom is equal to, or you can write R is equal to A by 2. So this is how you can represent that. And here you have this cube, this entire length is A, and here you have one cell, and here you have another cell. So make it almost the same, similar, which gives you R is equal to A by 2. And the packing fraction, this is important. Packing fraction for a simple cubic cell is either pi by 6 or 52%. Packing fraction, and what is meant by packing fraction? It is volume of atoms divided by volume of the cell. Coming to the second type of cubic crystal, that is body centered cubic. We can write the translational vector T is equal to n1 times vector A plus n2 times vector B plus n3 times vector C, where A, B and C are lattice parameters or lattice vectors. Now what are these lattice parameter? A is given by A by 2, where A is the side, one side of the cube. So A by 2 into y cap plus z cap minus x cap. Okay. Now lattice parameter B is A by 2 into z cap plus x cap minus y cap. Vector C is equal to A by 2 into x cap plus y cap minus z cap. Now volume of the cubic crystal is A cube by 3, and number of atoms is equal to 2, because in the cubic crystal we have, this is body centered, one at the center and all other atoms placed at the 8 corners of the cube. So 2 atoms, so this is not A cube by 3, this is A cube by 2. Now this is number of atoms or number of lattice points. Number of lattice points or number of atoms are same, and the coordination number equal to 8, and radius of this atom as given by radius is equal to r is equal to root of 3 by 4 times a, where a is the lattice constant. Okay. Now what is this volume equal to a cube by 2 represent? Volume is given by lattice constant a cube. This is, since it is cube, we can write a cube divided by n, which is number of atoms. Now this represent volume of the cube or the cell such that number of atom equal to 1. That means for one atom, what is the volume occupied? Now a cube is the volume occupied by 2 atoms. Then for one atom it will be a cube by 2, or you can also write it is the volume of the primitive unit cell. Now packing fraction is equal to root 3 by 8 pi. So this will constitutes around 68% of the total volume. Some examples of body centered cubic crystals are sodium, potassium, chromium, etc. FCC crystal or face centered cubic. Now here we need to write down the vector, that is the translational vector, which is equal to n1a plus n2b plus n3c. Now what are a, b and c? A, b and c are lattice parameters given by a is equal to lattice constant a by 2 into y cap plus z cap. Lattice constant b is equal to lattice constant a by 2 into z cap plus x cap. Lattice constant c is equal to a by 2 times x cap plus y cap. Now here the number of atoms in face centered cubic crystal n is equal to 4. So volume of the primitive unit cell, volume of the cell is equal to a cube by 4. Okay, so coordination number equal to 12, and the packing fraction packing fraction as equal to pi divided by 3 times root 2, which is equal to 74%. Coming to the radius of the atom or the molecule, radius r is equal to a by 2 root 2. Hexagonal closed pack structure. Now the vectors A is equal to root 3 by 2 ax cap plus a by 2 y cap. Vector B is root 3 by 2 ax cap plus a by 2 y cap. C is equal to cz cap. Volume of the crystal is root 3 by 2 a square c. Number of lattice point equal to 6. That means number of atoms. Coordination number is 12, and for there is a concept called ideal hexagonal closed pack structure, HCP. Then for ideal HCP, C by A ratio should be equal to root of 8 by 3. Packing fraction is equal to 74%.